In the previous episode, we learned that to find planets that can support life, we have to understand the stars that host them, especially the ultraviolet light those stars emit. But to see that ultraviolet light, we have to get above our own atmosphere. And the fastest way to do that is to launch a rocket. We're here in Australia, and we're gonna launch some rockets. We're following two NASA rocket missions as they try to understand how stars make the planets around them suitable for life. I'm Miles Hatfield, and in this episode, we're gonna see what it takes to get a sounding rocket into space. If you ask me, sounding rockets are NASA's true MVPs. Their name comes from the nautical term to sound, meaning to measure. No astronauts here. These rockets specialize in carrying scientific instruments. They take short flights, spending just a few minutes in space before falling back to the ground for recovery. Scientists can then relaunch the same instruments again, and again, and again, adapting them to new purposes. It makes sounding rocket missions far less expensive than other alternatives, and a lot faster to develop, too. Many scientific firsts are achieved with sounding rockets because of their quick turnaround time. In fact, the two missions we're following, Sistine and Deuce, are breaking their own scientific ground. The ultraviolet light they measure could reveal whether sun-like stars throughout our galaxy are capable of supporting habitable planets. To get their instruments to space, they're relying on the experts from NASA's Wallops Flight Facility, who operate over 20 sounding rocket launches each year from locations all around the world. Still, no matter how many launches you have under your belt, there's one wild card that can undo even the best laid plans.
Roughly an hour and 15 minutes before launch, we start doing balloons every 15 minutes, and that's giving us those low-level winds. The closer we are to the surface, the more sensitive the rocket is to the impact of the winds.
For NASA's range and launcher teams, getting into space is only half the battle. These low-level winds will also affect where the rocket lands.
It's a suborbital rocket, so we go up and we come down. I'm required to keep the rocket within the hazard area because that's what we alert the public to stay out of, and we clear it, and that's kind of the box that we have to play in. You know, we're trying to aim a point that's downrange this way. We may have to point over here so that when the winds go up, it'll come up and impact there.
Using computer simulations, the launch team has figured out exactly how much wind the rocket can take without risking being blown off course. As launch approaches, Brittany keeps a close eye on the real-time wind measurements to be sure they stay within an acceptable range.
But it gets really exciting. In the final 2 minutes, you will see me and Mike with our eyes glued to that monitor and my finger on the button for my comms. You know, we're the ultimate safety authority. It's our judgment call if the winds are trending out or if that was just a random data point and we can proceed.
Once the rocket is in the air, a whole slew of internal systems need to kick into high gear. I caught up with the Sistine science team as they were running the final sequence tests, simulating everything that will happen during the flight.
We simulate starting about 10 minutes before the launch itself, and we run through all of the steps you would, exactly as you would.
And the countdown clock has started.
90 seconds here, where we're about to hit T-minus 90, is my favorite part on launch night, which is where they're polling for the final go.
Go.
Yeah.
Go.
Where they're running through all the major subsystems and making sure that everything looks correct now, because this is the last chance to say that there's a problem before you're just assuming we're rolling into launch. First stage would have ignited first, and it's already burned out by 6 seconds. And then our black branch starts, which is the second stage. As you're launching, you want to be spun up, but then you want to stop that spin once you're observing.
What would happen if you guys didn't stop spinning?
Would probably be catastrophic.
Let's hope that doesn't happen.
And we prepare for the shutter door to open.
Whoa. There it is.
So shutter door opens. Towards the center there, this black camera is our star tracker. And so that right now is figuring out where it is in the sky and then driving us over towards our target. There you can see our big primary mirror. And then this kind of X structure you see up front is holding our secondary mirror, so the second optic in our telescope. And now we're hopefully celebrating. or talking about whatever went wrong during the flight at the same time.
Yes.
Once the payload has been fully tested and confirmed ready for flight, they bring it down from the payload assembly building to the launch rail, where it will be connected to the motors. This is the last place this experiment will sit on land before it launches into space. As night falls over the Arnhem Space Center, it's time to hope for good weather. If all goes well, we'll soon be high above it. Next time, the thing you've all been waiting for. It's gonna get pretty loud.